So this topic is something that's kind of notoriously difficult for students to wrap their heads around. But in my opinion, the more I look at it, the more interesting it actually becomes to me. When I first learned it, I thought it was impossible and didn't make any sense. And now that I've taught it so many times, it's slowly starting to make more sense. And that might be kind of disheartening to the rest of you, but it is what it is, and we're gonna do our best. So I'm going to. I'm going to try and intuitively describe this process of change of variables using stuff that we already know, okay? And so the idea behind change of variables is basically that this is the generalization, okay? This is the generalization of what we have been doing when we've been solving stuff in X and Y land, okay? We've been solving stuff in X and Y land, and we've been getting away, when we're talking specifically double integrals, we could do it using polar coordinates, for instance. And if we needed to, say, integrate over some region over here, okay, some region, some circle over here, we found that usually if we let r go from, say 0 to whatever the radius is, and then we let theta go from 0 to 2 pi or something, we could basically create a transformation that says, look, if you give me some combination of r and theta, and you give me some combination of r and theta for y, then what we've been doing is we say, look, if this is 2 pi, and let's say this is a circle with a radius 3 or something, then basically we could, instead of trying to execute a double integral over this area right here, dA, what we basically said was that we can just do a double integral over a rectangular region where r goes from like 0 to 3 and theta goes from 0 to 2 pi or something. And the only price that we pay to do this is that instead of just having, dr d theta or d theta dr, the price that we pay is this red little r right here, okay? This is like there was this little extra bit that came with us, okay? And so what we've been doing, and I haven't been calling it this, but what we've been doing is we've been using these pre-made transformations that take us from r and theta. Okay, so you give me an r and a theta value, and I tell you what the x is from it, and I tell you what the y is from it, right? And in our brains, you're saying, well, no, Dylan, we've been starting here, haven't we? Haven't we been doing like a double integral of something dA, and this is our region, and we've been trying to go backwards and solve it over here? No, actually, what we've been doing, that's what I've led you to believe, but you're going to have to put that, on hold for a second. What we've actually been doing is we've been working backwards this entire time and trying to think, what would these bounds be, right? What would these bounds be in r and theta land, such that if we use this transformation, okay, aka if we use a really nice rectangular region of integration, it is going to give us the same answer as if we had integrated it over this circular region in our good old-fashioned rectangular coordinates. And we've had to work backwards every time, right? I've given you the transformation. We've said, okay, we were using polar coordinates, and every single time we've had to kind of think backwards and start with, let's figure out what these bounds are such that we go through the loop and end up over here. So we have been working with I'm going to start putting a word to it, a transformation that takes us actually from r theta, right? Takes a really nice rectangular region. We use the transformation given by x is equal to r cosine theta, y is equal to r sine theta. It gives us a circle, right? It transforms this rectangular region here into a circle over here. And then we use that information to kind of, we have to go backwards in a sense to construct, right? We don't know what this rectangle is, right? We don't know what those points are yet. We don't know what these bounds are. And we say, look, we know that's a transformation we want to use. So we have to kind of think backwards using an inverse transformation, which we don't ever write out, but I'll talk about this more a little later, okay? And we've kind of just had to think backwards, okay, if it's a circle of radius 3, 0 to 3. If it's theta goes, if it's a full circle, it's 0 to 2 pi, right? And then we're like, oh, okay, this isn't so bad. That's a 3, that's a 2 pi. Now I can solve this integral, and these two are the same so long as we pay the price of this r right here, okay? And so if this is a little confusing, let me try to, give you something else. Okay, we do the same thing using spherical coordinates as well, okay? So the idea is that let's say we have two coordinate systems, okay? And we have been trying to do math in the x, y, z coordinate system. We get some sphere, okay? Oh, please make a circle. Yeah. Okay, we get some sphere that has some radius to it, okay? And we said, well, let's use this pre-made transformation. X is equal to rho sine phi cosine theta, right? It's kind of like cylindrical coordinates, but instead of r cosine theta, it's rho sine theta. And instead of r sine theta, we have rho sine phi sine theta. And z is equal to rho cosine phi, right? Let's use this pre-made transformation that I just gave to you. And so, okay, well, why is that useful? I want to solve triple integrals over here in Xland using dv. And we said, okay, that's cool, but what bounds over here, can I filter through this transformation that are going to actually give me a sphere? And if this is a sphere of radius rho, we might say, well, this axis is rho, maybe this axis right here is phi, and this axis is the theta axis. So let's say this is a sphere of radius 2, then it's going to go out to rho is equal to 2, phi goes from 0 to pi, and theta goes from 0 to 2 pi. And it gives us a really nice rectangular kind of region of integration here, right? It gives us this nice rectangular region of integration, and that's why we get to use these really nice bounds of rho goes from 0 to 2, and phi goes from 0 to pi, and theta goes from 0 to 2 pi. And the only thing that we have to worry about, the only price that we pay making this jump is, we still get our d theta and d phi and d rho, kind of like what we expect, but there's this extra bit that comes out, this rho squared sine of phi, this kind of extra price, what we call maybe a distortion factor, if you will, right? Because remember that this nice little cube over here, dv over here looks like something, kind of like this. It's like a curved little box over here, right? And we said, okay, to go from one to the other, this nice rectangular region, there's this distortion that happens to our dv, right? And that distortion is this rho squared sine phi, right? That this dv over here goes and becomes the pink dv in our rectangular coordinates, okay? And so I mentioned to you that I've been kind of just giving you these transformations and saying, look, isn't this nice? This transformation takes a rectangular region and turns it into a sphere. And my goodness, isn't that nice? Because we can use it to go backwards, and we can also take spherical regions and turn them into nice rectangular regions back in rho, theta, and phi land, and we can solve these triple integrals. Isn't that nice? Isn't this so convenient? Okay, so this is what we've been doing. You have been given this every single time. But what happens when you don't have that region? Okay, and this is kind of what the notion of change of variables is all about. And so I'm going to draw, we're going to start off with just double integrals, okay, 2D regions of integration. And I'm going to try and keep this as general as possible. So let's pretend we have our x and y, and let's pretend we have, instead of r and theta or phi and rho or whatever, the book likes to use u and v as our two generic, variables. So back in, if we were doing polar coordinates, this would be the variable r and this would be the variable theta. Or if we decide to keep it in terms of the variables u and v, we might say x equals u cosine of v and y is equal to u sine of v, if we're, say, trying to talk about coming up with a transformation for, say, a circle, right? We would do, this is my 2 pi, this is r goes from 0 to 3, if this is a circle radius 3, and, voila, there we go. So the name of the variable doesn't really matter that much, whether u, v, r, theta, but we're going to use u and v because that's what the textbook uses. So here's the idea, the general big brain idea, talking double integrals only, okay? The idea is that we have some double integral that we want to execute over here in the rectangular coordinates, okay? It's over some region, some domain, let's call it R for region, okay? It exists over here. This is our region. It's some generic region. Notice it's not a circle anymore. It's not a bunch of straight lines. It's some weird generic, it's not 3D, this is a 2D region, okay? And it is a 2D region of integration. And the question is, well, Dylan, I feel scared. I don't know how to describe, right? What if I can't describe this region very well? Like just looking at it, like even if I give you these 4 points, okay? Even if I give you those 4 points, this one's curved, that one's curved, this one's curved, that one's curved, like how do you even describe the x and the y bounds for something that looks like that? Okay, how do you do it? And just like when we did polar, right, we said, hey, with circles, there's a special transformation that we use that said, look, if you use this transformation to go from UV land into XY land, you can also use it to go backwards, and it takes a circle and turns it into a rectangle. Wow, isn't that nice? But the problem is as you may have noticed, we don't have this transformation. We have a generic region R that we are trying to integrate over this region right here. Okay? But I don't have a transformation. So how do we go about doing this? Okay? So here's the idea. For the most part, what this section will do is it's going to give you a transformation. It's going to give you x, and it's going to give you some function of u and v, and it's going to give you y is equal to some function of u and v. And the point of this, okay, is what they're going to do is they're going to say, if, I have just a nice rectangular region in u and v, okay, let's say I have this, and let's say it's u goes from 0 to 3 and v goes from 0 to 2, okay, so u goes from 0 to 3 and v goes from 0 to 2, okay? What happens to this yellow region if I put it through that transformation? What does it look like over here in X and Y land? And you're like, Dylan, I don't know what you mean. Well, we found out that, for instance, if this was 2 pi, right, if I let v go from 2 pi, and I picked the transformation u cosine of v and u sine of v, we found out through experimentation and also me just telling you that this was a circle of radius 3, centered at the origin. Boom, that's what it did. And you're like, okay, cool, but what? Well, what do you mean, but what? This allowed us to basically, we were able to use this transformation to help us solve double integrals for circular regions, okay? And so the point of this section is that, we're not going to, our job is not going to be to come up with the transformations on our own, okay? That's not the job. The point of this is, hey, look, if I give you some transformation which involves u and v, and some transformation u and v for y, could you just tell me what shape is this going to create in x and y land? Is it going to give me a blob? Is it going to give me maybe a trapezoid, right? Maybe this will be a general parameterization for dealing with integrals that have trapezoidal regions of integration, right? The point is we are just going to play around with and experiment with, what do these random transformations do? What effect will they have, on our regions of integration? And this is, again, it's a little bit beyond our pay scale in this class to actually come up with these transformations on our own, because it took someone a lot of effort to figure out that r cosine theta and r sine theta was the perfect transformation that you needed to go from a nice, easy rectangular region of integration to a circular region of integration in x and y. Like, it took somebody a long time to figure that out. So we're not going to come up with that. We are simply going to play around and figure out, look, what is happening in UV land? What's it going to look like in x and y land? Okay. Now, in the next video, I will go over an example that deals with this, but I want to talk about something that I brought up before. And the thing that I brought up before was the fact that when we use a transformation, okay, when we actually go and use a transformation, okay, when this yellow region here becomes this region in XY and vice versa, right? If we go backwards, right, they're the same region, okay? So this is the region R over here. Technically, this is like the region S over here. That's how they do it in the textbook. I mentioned that when we look at the double integrals and the differences between them, the bounds are the easy part, right? These are the easy things to come up with. There's still a dv over here, right? There's a dv here and not a dv. We're in 2D, two double integrals. There's a dA over here and a dA over here. But what happens is when we go, right, when we turn this in from an xy integral into a uv integral and use the really nice bounds given by, say, u goes from 0 to 3 and v goes from 0 to 2 in this particular example, there is a distortion factor, right? There's a different, remember, a dA over here looks like this. It's like a small little chunk here. And a dA over here is a nice rectangular region, easy peasy. So clearly, they're not the same. They're close, but they're not the same. And so there's this distortion factor that slightly modifies what dA is when we make this jump. And we call that the distortion factor, okay, the distortion factor that kind of changes the size, the size of dA. Okay, the distortion factor that changes the size of dA is called the Jacobian. Okay, it's called the Jacobian. And you're like, wow, have I ever seen this before? Absolutely you have. Let me show you the different ways you've seen it, okay? In one-dimensional 2D calculus, okay? Way back in the day when we were doing integrals of f of x dx, okay? and we needed to use a u substitution. Okay, we said like, let u equal blah, right? We transformed that integral into something with respect to u, right? It was like x in terms of u. This was a function now in terms of u. And what happened? Well, we had a du, right? Like the dx became du, but there was like this extra little bit here, right? There's this like little dx du bit, right? This right here was part of the Jacobian all the way from calculus 2, right? This right here used to be the Jacobian, and in one dimensions, it's very simple to come up with. In 2 dimensions, we might have taken, let's say if we were going into polar coordinates, we would take a function f of xy dA, and we would do some parameterization, and we would end up over here with a function in terms of r and theta. So technically they might write it as x in terms of r and theta like this, and y in terms of r and theta like this. But just for making things nice, I'm just going to write it. It became a function in terms of r and theta. We still had a dA, but what price did we pay? What was that distortion factor? Well, the distortion factor was this r term right here. This right here was our Jacobian, okay? And this is a Jacobian based on r and theta, okay? This earlier Jacobian was just a Jacobian based on u, okay? And then in 3D, so let's do the 3D case. So in 3D, we might have taken a function that's in terms of x, y, and z, dv, and we did some sort of transformation. And what did we get? Well, let's say we were using spherical coordinates. We would get a function in terms of rho, theta, and phi. We got our own dv, right? Which is, the d rho, d phi, d theta. But what else came with it? We got this rho squared sine of phi. And this was our Jacobian based on rho, theta, and phi. Okay, this was our distortion factor. This is the back and forth price that we pay to go from a really nice region of integration and a really nice dv into one that wasn't so nice, right? So for a sphere, I think it looked something, my drawing skills, a lot to be desired. I think it looked something like this, right? Something like that. Okay, slightly different areas. So I would usually, whenever I showed you this, I would show you this geometrically. I would draw it for you, and I would say, look, we can kind of see from our drawing that this intuitively makes sense that these are the Jacobians, right? Oh, the reason that our dv in rectangular coordinates, or our dA, becomes an r dr d theta, or a rho squared sine phi d rho d phi d theta, right? I showed you those in the last video and gave you a pretty easy, intuitive explanation by just drawing a picture. But I'd like to go back here and talk about, why this makes sense, okay? So let's kind of revisit. I'm going to erase some of this and just kind of revisit this drawing up here, okay? So remember, the idea is that we're going from uv to xy via some transformation, because when we have that transformation, we can use it to go the other way, basically get an inverse transformation. Hooray, okay? And so here's the idea of where this thing called the Jacobian, where this thing kind of comes from. So this part of the video is going to require that we remember our 3D calculus, and especially working with vectors. So we can describe, our transformation. We can describe our transformation using vectors, okay? And specifically, we can say that the transformation is this vector function in terms of u and v, And we can say that basically the x component is g of uv, and the y component is h of uv. So the idea here is that this transformation, right, is mapping all of our points from uv into xy. And specifically, right, what we're currently interested in is on a microscopic scale, right? This isn't 3 and 2 anymore. This is a microscopic scale. The question is, what is the difference between this area over here, right? This dA over here versus this area over here, okay? So these, even though I have it drawn really large, are supposed to be microscopic in scale. The question is, what is the difference between these dAs? What are their areas? And so hopefully we remember from Calculus 3 that if this transformation takes the point u0, v0, and maps it to x0, y0, that I can create, right, if the goal is to estimate the area of this shape, right, what is that dA? I can create two tangent vectors, okay? I can create a tangent vector going this way, which we'll call, it has a special name, we'll call r of u0 comma v, and I'll explain what this is. And we can take another vector this way. And what are these coming from? We're taking the partial derivative of this basically vector function with respect to u and with respect to v. So this is the vector function where we have u and then we fix v0, okay? So this is so maybe I'll write this down. So from Calc 3, we get basically two tangent vectors to x0 and y0. And if we get two tangent vectors to x0, y0, we can actually create a parallelogram and come up with the area of this parallelogram. And on a microscopic scale, the area of this parallelogram and the area of this curved dA are the exact same thing. Okay, so what are those two vectors, by the way? What are these r sub u's and r sub v's? Right, this right here is r sub v, and this vector right here is r sub u. What is that? Well, r, right, so let's remember r sub u is going to be equal to the vector. Well, let's take some partial derivatives, and we're going to get dx, right, dx du, and dy du. And then if we take the partial derivative with respect to v, our other vectors should be dx dv and dy dv. Okay, so if we have these two vectors, if that's what those two red vectors that I drew up there basically represent, how do we come up with the area? Well, we should remember that the area of the trapezoid, or excuse me, not of trapezoid, of the parallelogram is equal to the magnitude of the cross product of those two little tangent vectors right there. Well, what is that going to be? Well, this isn't going to be that bad. We can do this pretty quickly, right? If we put in the two little vectors, we put in like dx du, we put in dy du, and then we can put in dx dv, and we put in dy dv. And if we do this, we're basically going to get, what are we going to get? We're going to get dx du dy dv minus dx dv times dy du, right? And this right here, I claim, is basically the difference, right? This right here is the Jacobian, okay? This is the Jacobian. This is the difference. This is the distortion factor between this area over here and this area over here. Now, maybe you're just like, it's not clicking yet, and I don't blame you. But let me give you something that you've definitely seen before 100 million times, which is, what is the Jacobian of the polar coordinate transformation, right? What is that, okay? So you're like, okay, well, so from polar coordinates, okay, our transformation just in vector notation is via r and theta, right? And it's going to be the function r cosine theta, r sine theta. That was our transformation, okay? And if we take the partial with respect to r, right, what are we going to get? Well, if we take the partial with respect to r, we're going to get the vector cosine theta and the vector sine theta. And if we take the vector with respect to theta, right, if we take the partials with respect to theta, we are going to get negative r sine theta, and we're going to get r cosine theta. And what happens when we put this into our little Jacobian formula that I just came up with there, right? We took the very generic formula, right? This very generic, like, hey, that's what a transformation looks like in general. Let's see what the Jacobian comes out to be, right? So if we put in these partials, right, we take the magnitude of the cross product of these, okay, this ends up just becoming, well, we're going to put in cosine of theta here. We're going to put in sine theta here. We're going to put in negative r sine theta here and an r cosine theta here. And if we do this, right, what are we going to get? We're going to get an r cosine squared theta minus a negative, so a plus r sine squared theta. And holy smokes, we can factor out an r and get cosine squared theta plus sine squared theta, which indeed just leaves us with r, which is this distortion factor, okay? This distortion factor that changes, what our little dA is going from one coordinate system to the other coordinate system, okay? Now you can extend this into 3 dimensions very easily. If you would like to, you can do the one for spherical coordinates to verify that the Jacobian for spherical coordinates is indead rho squared sine of phi. But I think this is enough for us to kind of, start wrapping our heads around that what we are going to be doing in this section is we are going to be given a rectangular or maybe not so rectangular, and as we'll see, but we're going to be given a nice simple region of integration in u and v, and we're going to be given a transformation of x and y. So we're going to put in u and v and get out x and y, and our goal is to simply figure out, look, what the heck shape is this going to look like in x and y, and what is the Jacobian going to be if I wanted to use this transformation to help me do some integration. Okay, that's going to be our goal. So this video is just to serve as an intuition. It's like, okay, I kind of maybe sort of see the idea kind of hanging on by a thread. We're going to do some examples in the next couple videos, and then it should start to feel a little better. So watch this video over once or twice, and then head on over to the next ones to do some examples.